Selamat sejahtera diucapkan kepada Dr. Mashta. Saya Lok Juta dan akan membentangkan projek kita yang bertajuk Block Size and its Impact. So, sila benarkan saya untuk gunakan bahasa English untuk membentangkan yang seterusnya. Introduction. What is SMP Cache? SMP Cache is a trace-driven simulator for the analysis of teaching of cache memory systems on symmetric multiprocessors. So basically, this SMP cache is what we use along throughout the project. Okay, so the simulation is based on a model built according to the architectural basic principles of these systems. The simulator has a full graphic and user-friendly interface, and it operates on PC systems with Windows. Cache memory. Cache memory is a special, very high-speed memory. It is used to speed up and synchronizing with high-speed CPU. Cache memory is costlier than main memory or disk memory, but economical than CPU registers. Cache memory is an extremely fast memory type that acts as a buffer between RAM and the CPU. It holds frequently requested data and instructions so that they are immediately available to the CPU when needed. Cache memory is used to reduce the average time to access data from the main memory. The cache is a smaller and faster memory, which stores copies of the data from frequently used main memory locations. There are various different independent cache in a CPU, which store instructions and data. Okay, so this figure shows the 2D structure of the main memory system, including the CPU and different levels of memory, such as cache memory, primary memory, and also secondary memory. Levels of memory. Level 1, register. It is a type of memory in which data is stored and accepted that are immediately stored in CPU. Most commonly used register is accumulator, program counter, address register, and etc. Level 2, cache memory. It is the fastest memory which has faster access time where data is temporarily stored for faster access. Level 3, primary memory. It is memory on which computer works currently. It is small in size, and once power is off, data no longer stays in this memory. Last one, level 4, secondary memory. It is an external memory which is not as fast as main memory, but data stays permanently in this memory. Cache performance. Okay, when the processor needs to read or write a location in main memory, it first checks for a corresponding entry in the cache. If the processor finds that the memory location is in a cache hit has occurred and data is read from cache. However, if the processor does not find the memory location in the cache, a cache miss has occurred. For a cache miss, the cache allocates a new entry and copies in data from main memory. Then a request is fulfilled from the contents of the cache. The performance of cache memory is frequently measured in terms of a quantity called hit ratio. So this is the formula of the hit ratio. For simulation task. Okay, so this is the overview of our task. For our task, we are asked to show the influence of the block size on a miss rate. The memory trace set that we used are CXP, COMP, and EAR respectively. The architectural characteristics of the configurations of the system listed below are remain constant along the process of doing the project. Okay, Task 1. Okay, so for this task, we are asked to configure the words by blocks using the following configurations, starting from 4, which block size equals to 8 bytes, to 1024. Block size equals to 2048 bytes. And for each of these configurations, we need to obtain the miss rate using the trace files CXP, EAR, and COMP, which we mentioned before. Okay, so this figure is the screenshot that I took, which shows the miss rate of the configurations of the words by block from 4 to 512. This is because during the project we found that the miss rates for these configurations of the words by block remains the same. Okay, totally same. So as we can see, for the global miss is equals to 26.471%. And this figure shows the miss rate of the configuration of the words by block for 1024. Okay, as we can see, for the global miss, it is equals to 29.412%, which is slightly higher than the miss rate before. Okay, so this table is just it's the same, just that it shows the global miss rates for the block size varies from 4 to 1024 clearer. Okay, so now we are going to use memory trace set EAR. From memory, for number of words by block 4 to 256, sorry, the miss rate decreases gradually. However, the miss rate started to increase again, starting from number of words by block equal to 512 to 1024. Okay, so this table shows the global miss rates as the block size varies from 4 to 1024 for memory trace set EAR. Okay, as we can see, for number of words by block equals to 4, the global miss rate is 13.583%. And as we increase the number of words by block until 256, the global miss rate keeps decrease gradually until 3.429%. And starting from number of words by block equals to 512, it started to increase again to 6.274%, and 1024 number of words by block, it increased to 13.922%. Task 2. For this task, we are asked to observe the relationship of the miss rate and the block size. So, for memory traces set CXP and COMP, the miss rates remain the same for number of words by block from 4 to 512. However, it increases at the number of words by block equals to 1024, which happens for global writing, while miss rates for global reading remain the same. For memory trace set of EAR, the global miss rate decreases gradually by the increase of number of words by block from 4 to 256. However, it started to increase again at number of words by block equal to 512 and 1024, which happens for all the benchmark. Discussion. For the cases using CXP and COMP, the miss rate increase when the number of words by block increases to 1024. And after we do some searching, we found that this is because as block size increases, the number of sets in a fixed size cache decreases. And also this increasing the probability of conflicts, and hence the miss rate is increased. While for the EAR case, the miss rates for number of words by block from 4 to 256 decreases gradually. This is because the larger size of the block size can take advantage of the spatial locality, which is that all those instructions which are stored nearby to the recently executed instruction have higher chances of execution. The advantage of a block size greater than 1 is that when a miss occurs and the word is fetched into the cache, the adjacent words in the block are also fetched. Therefore, subsequent accesses are more likely to hit because of spatial locality. Hence the miss rate is decreased. However, a large block size means that a fixed size cache will have fewer blocks. This may lead to more conflicts, increasing the miss rate, and this is why the miss rate started to increase again, starting from number of words by block equal to 512. Okay, so in a nutshell, the compulsory misses will decrease when the block size is enlarged. Cache pollution does not appear while this experiment is conducted. Task 3. Okay, for this task, we are asked to observe the relationship of the block size and the system performance. In overall, for the memory traces set CXP and COMP, the increase of block size did not affect the system performance and the process was fast. However, for the memory trace set here, the process took a few seconds, which is longer than the execution time of the memory trace set of CXP and COMP. Also, as the block size increases, the system performance also slightly decreases. This is because the larger the block size, the larger the miss penalty, which is the time required to fetch the missing cache block from main memory. Okay, so for our conclusion is simple and short. In conclusion, the block size does affect the miss rate in certain cases. And from this project, we get to know the basics of the SMP cache and its function. And also, the focus for this project is mainly on the relationship between the block size and the cache performance. And in the process of doing the simulation experiment and to find the reasons of the situations occurred, such as the decrement and increment of the miss rates, and also the reasons that cause that, the causes. Okay, so we also learn more details about the cache memory system. So this is the end of our presentation. Thank you.